Welcome back. So, we shall continue our discussion on light matter interaction. Here we are going to particularly look at matter which we call as molecular matter or molecular material. So, before we discuss this molecular matter, we need to understand in what different ways energy, light is a form of energy, you can say, light can be interacting with the molecules. So, there are 4 different ways in which the energy of molecules can be divided, and thereby light can interact per se with at least few of them. There is the electronic energy of molecule. Electronic energy simply means that you supply energy to the molecule. That energy allows light, that energy allows the electrons present in the molecules to move from lower level to upper level. That is simply what electronic energy means. Vibrational means you supply some amount of energy to the molecule, and this complex molecule will have some sort of a vibration, like you are seeing in the GIF. This is called scissoring. There are several other of these vibrational moments, antisymmetric stretching or rocking or different ways. In all these different molecules can move independently of one another upon excitement by light. There are rotational and translational. Rotational is mostly stereoisomers, where there is a chirality where these molecules are not exactly mirror image to one another, and translational is simply when you supply energy to a molecule and the phase of the molecule changes. So, consider you are boiling water. So, it is converting it to steam, okay. Ice to water to steam, all 3 different phases of matter, all 3 different phases of molecule. It is not actually quantized. So, this is the 4 different ways in which you can classify the overall total energy of molecules, and thereby you can supply external energy into it to give it. Rotational is simply when you are rotating at a particular symmetry, different from vibration. For biophotonics purpose, we strictly stick to electronic and vibration. Translational, it is not even quantized, we are not going to discuss that. Rotational, we may discuss this at the end, but for the time being, for all intent and purpose, your life will be very easy if you stick to electronic and vibration. That are the different types of energy of a molecule that we are going to deal with for a couple of more chapters. If and when rotational energy comes, I will bring it in. For this lecture at least, let us discuss electronic and vibration. Electronic energy, where electrons are involved; vibrational energy, where the whole molecule or the whole atom is involved. There is this thing called vibronic energy, where both of them are involved, because obviously when you are supplying huge amount of energy, different types of energy, different types of wavelength, not just one wave but multiple wavelength, you are agitating both the atom, both the molecule per se, as well as the electrons that are present inside those molecules. So, let us go through it. So, molecular materials, we know pretty well, we have discussed this image, that the atoms, the quanta, the discrete level of the orbitals of the atoms overlap. You have different types of bonds, and overall the atomic orbitals merge together, overlap together, and we form hybridized orbitals, molecular orbitals. We have known this. Molecular materials, i.e. organic materials per se, biological materials you can discuss, mostly deal with saturated materials or conjugated materials. So, molecular materials can be divided into saturated materials and conjugated materials. Saturated materials, in which a chain type of molecular chain is formed where they are very strongly bonded with one another. Huge amount of energy is required, and that energy only displaces the electrons per se. The atoms are very rigidly bonded, and it's basically like your transparent plastics, right? Any energy lower than wavelength of ultraviolet is simply passed through it, simply transmitted through it. Ultraviolet only are able to generate some amount of reaction to it. Saturated materials are these plexiglasses, polymethyl methacrylate. They are, for all intent and purpose, as even stronger than glass and as transparent as glass. We are not going to discuss about that. We are mostly discussing about the conjugated materials, the conjugated molecular materials. What conjugated molecular materials are? This is a perfect example of a conjugated materials where the molecules in themselves, carbon, hydrogen and nitrogen in themselves, are very strongly covalently bonded. So, a molecule is formed with set of atoms, and these atoms are very strongly joined together as a molecule. But this set of molecule is very weakly joined with another set of molecule. Understand this. This is the fundamental difference between saturated and conjugated. Saturated, every atom, every molecule is very strongly bound with one another, and thereby this is a very strong chain. Tensile strength, all those things increases. Just look at windshield of your car. You know, the first windshield that you have that is not made up of glass, that is actually made up of polymethyl methacrylate, PMMA. But conjugated materials are very soft. Conjugated materials are very soft because though the individual molecules are very strongly covalently attached, each molecule is attached with another molecule with the weakest chemical force, the van der Waals forces. Van der Waals forces are happening because of the random fluctuation of the electron cloud, and they rapidly falls with distances. So, molecular materials, especially conjugated molecular materials, are very soft to touch, very soft bond, and they have low melting point. Take any organic compound, look at yourself, how much heat different part of your body can sustain, how soft it is, and thereby understand that what I mean by biological materials which are conjugated. However, remember this fact that individual molecules are quite strong. Individual molecules are quite strong. Perhaps one of the reason why when we go below few molecules, couple of molecules, it is very difficult to affect them, destroy them and get rid of them if they are causing any problem to your health and safety. But anyways, let us discuss little bit more about these conjugated molecular materials. So, they contain the idea here is that if we understand individual molecules, we will be more or less able to understand the whole material, because whole material is overall made up of loosely connected molecules, van der Waals connected molecules. So, if we understand the optical property of molecule, we can simply average it out and thereby determine the overall property. So, when we are talking about individual molecules, as I discussed, each atoms of this individual molecule have its own orbitals where the electrons are probably found, and when they come together to form a bond, their atomic orbitals overlap and you have a ground state and you have a higher energy state. So, the idea that I have discussed, you already know that when we supply some amount of energy has been supplied, one of the electron moves from lower level to the upper level whenever some amount of, and this is absorption as we discussed. Whenever this electron at the upper level after spontaneous emission comes back to the original level, photon may or may not be emitted. Okay. Remember previous lecture, may or may not be simply emitted. So, that is overall thing, life is good, life is fine, we have understood. Turns out there is little bit more complication to that. You see, when we are talking about the electronic states in conjugated molecules, it not just we are talking about one energy band or two energy band. What exactly are these energy bands per se? Turns out that each of these energy bands contain huge numbers of individual molecular orbitals. What do I mean? I mean that you have a particular molecule, that particular molecule have molecular orbital. Then you have another molecule coming closer to it, another molecule coming closer to it, another molecule coming closer to it, and as such infinite number of molecules have joined together, weakly so, but they have come very, very close with respect to one another. When they have come that close with respect to one another, their molecular orbitals starts overlapping. However, when I talk about overlapping, here it needs to be understood that throughout the bulk material, though the molecules are very similar, in fact same with one another, all the molecular orbitals cannot simply collapse into one single molecular orbital. Understand this point. There is a molecule, there is a molecular orbital where the electrons of the entire molecule moves. You bring in another molecule towards it, another molecule towards it, another molecule towards it. So, all of their molecular orbitals will overlap, but it will still have a minor difference between one another. It cannot combine into one single molecular orbital. Why? Because then it will violate the Pauli's exclusion principle. Remember, we cannot have one single orbital for these n number of electrons moving around. You have to have some amount of difference. So, thereby if you are looking into a band, that is the reason why we call them band, all these individual molecular orbitals of individual molecules come together, they have very similar energy level, though they are nominally discrete, and they merge together to form, instead of one single energy state, one single molecular orbital, they form a band. Consider this as a highway. Consider this as a highway. Very small number of streets, large number of small streets are merging together to form a highway. A highway is one total single thing, but it has lanes. But it has different lanes. You can transfer from one lane to another lane easily. You can transfer from one lane to another lane easily. If this is your upper level, this is your lower level. Within the upper level, you can transfer very easily between lanes. Within the lower level also, you can transfer very easily between individual lanes. But transferring from upper level to lower level is difficult. And how this has happened? This has happened, this highway, different lanes have formed. How highway has formed? Because of the merging of individual very small streets. Large number of narrow streets have combined together to form a band. Okay, they still have discrete energy value. The discretion is never going anywhere. These are individual levels. No E1 has not been divided into E1.1, E1.2. They are still discrete. They are still whole number. But E1 actually is a proper total band which covers an entire range of energy. Say 5 electron volt to 5 electron volt to 10 electron volt. Say I am just using very metaphorically, not to take literally. Okay, and 5 electron volt to 10 electron volt, you have individual lanes, individual paths where electron can exist. Now, if electrons can exist in any of these individual orbitals, it is very easy for them to move around up to down without much of a problem. It is like you are driving a car in the lane of a highway and you can simply change the lane in particular direction of the highway, but if you have to change the highway altogether, you have to go through the you have to take some measures. So, the lowest value of the the highest value of the ground state is the minimum energy, we call it HOMO, which stands for highest occupied molecular orbital. This is the highest occupied molecular orbital, and LUMO stands for lowest unoccupied molecular orbital. This is for the excited state. E0 is the ground state, E1 is the excited state. The minimum of excited state is LUMO, lowest unoccupied molecular orbital, because when in ground state, normal cases, this E1 is completely unoccupied, though there are several berths, several seats available, but there are not enough passengers meaning electrons. And HOMO stands for highest occupied energy level, ground state, where there are also several levels. In these several levels, usually electron tend to occupy the lowest seat, but if we are discussing about the gap between E0 and E1, we actually are looking for the gap between highest occupied molecular orbital. This is the highest energy you can get in a ground state. HOMO is the highest energy an electron can get in ground state, where LUMO is the lowest energy an electron can get in excited state. The gap between LUMO and HOMO, electronics engineer students will laugh at it, can be considered as band gap. Electronics engineers, people who deal with semiconductors these days, consider this as valence band and conduction band. I could clearly see that you figured it out. HOMO and LUMO stands for valence band and conduction band. Why the change of the name? Well, HOMO and LUMO is mostly to do with chemistry, organic chemistry. Organic chemistry people or the chemistry people usually like to deal with molecular orbitals, whereas I am an electronics engineer, we discuss more about valence band and conduction band. But remember, valence band and conduction band is specifically to semiconductors, right? HOMO and LUMO is this vast array of insulators, organic compounds per se. So, now remember, previously we were discussing simply changing an electron, moving an electron from upstairs to downstairs to upstairs, moving it up. Turns out there are various rooms both downstairs as well as various room in upstairs. So, now we have to be bit more specific. It is not simply we are taking the stair moving from below to up. We now need to understand which part of below, which part of ground state you are moving to. Okay, I am giving you the analogy. Consider a duplex, consider a house which has 2 stores. You take the stair to go from lower level to upper level, but here I am becoming more specific and I am saying that how much energy you need to go from which specific room of the ground floor to go to which specific room of the first floor. This is my simple analogy. You can laugh at it as you want. So, usually when we supply some amount of external energy, here we are giving say a particular frequency of light which matches with the absorption frequency. Light moves from electron can move from a specific level inside that E0, a specific room of the ground floor to a specific room of the first floor. Now, it has moved to a specific room of the first floor, specific room of the higher energy level. It can move within different rooms at first floor. It is like again another analogy. Once you have come to a highway, you can change the lanes within that same highway. 5-lane highway you can change just simply moving. So, it can simply move back to the LUMO position. Everything wants to return back to the lowest energy state available. You have excited electron from low energy to high energy, but high energy is divided into several subsections. Some of them are higher, some of them are lower. It can therefore tend to move back to the lowest unoccupied molecular orbital. If it is occupied, it cannot move like anything else. And then from the lowest occupied molecular orbital, it can return back to the original HOMO, that is highest occupied molecular orbital, that is the ground state, resulting in an emission of photon. From the HOMO state, highest part of the ground state, it can simply again come back to the lowest LUMO, lowest occupied molecular orbital. What does that mean? Electronics engineers will simply think that I am overly complicated things. Previously, electronics engineers simply thought about moving electron from valence band to conduction band and current will flow. It is bit more complicated in case of conjugated molecules. Conjugated molecules have subbands. Conjugated molecules have large number of these subbands, orbitals, molecular orbitals within each band. So, it becomes complicated and it is not straightforward. I go from lower energy to higher energy and higher energy to lower energy. If that would have been case, whatever has been consumed, whatever photon has excited will be emitted. But this is not the case here. Here, whatever photon has been absorbed given by this particular frequency, a part of it is lost while traveling inside the higher energy band. Understand this. In conjugated molecules, the absorption photon and the emitted photon are of different energies, different frequencies. Almost, well, a majority of cases, the emitted photon is at lower energy, lower frequency than the absorbed photon. Yes, because the electrons that the electron that has been excited by the photon has spent some of its energy roaming within the higher energy level, roaming within the lower energy level. This is the primary difference between the valence band conduction band theory of semiconductors with respect to the electronic state in conjugated molecules. Now, here the different phenomenon that happens are 1 and 3 are quite straightforward, absorption and emission is happening. 1 and 4, absorption and emission. 2 and 3 are non-radiative relaxation. What does this mean? This is again that phonon thing which I said. So, once the electron is in an upper level and it has to move somewhere below in the upper level itself, it can lose energy in the form of heat or it can lose energy in the form of vibration. Okay? It needs to lose energy, that is its nature. It has to somehow dissipate its energy. Within a band, within bands, the electrons can lose energy without emitting any photon. It can lose energy by simply dissipating it as heat or some kind of a vibration. This is the fundamental difference between semiconductor based conduction band valence band transfer of electrons or electrons, charge carriers, and organic compound based carriers, where the energy band is quite thick and they each contain subband, right. Consider these are different rooms of first floor and different rooms of second floor, or different rooms of ground floor and different rooms of first floor. Americans will consider the ground floor as first floor. So, there are 3 major states that are available here. Probably I should have discussed this at the fluorescence part, but let us understand this nevertheless, because this will set up the tone for my next class. So, you have a ground state where electrons are present at different levels. Okay. the electrons have to be spin paired. Here we are discussing about spin. Spin is another fundamental property of subatomic particles, specifically electron. Apart from mass and charge, electrons also possess spin. Remember spin quantum number from your, I think, high school physics. Everybody has gone through all those different quantum numbers. The last one is spin quantum number. The spin quantum number, spin is one of the two angular momentums, the other being orbital angular momentums. So the spin, since Pauli's exclusion principle, no two electron will have the same, all four quantum numbers in the same atom. So at the same orbital, the electrons have, you know, anti-parallel, how to do it, yeah, anti-parallel spin, right. So when you excite, say, one of the electron to move from HOMO to LUMO state, it goes to this particular position. It is still paired. Previously it was like this. I will go to the green background, yeah, blue background, yes. Now it has moved like this. This is excited, but still anti-parallel to one another. That is called the singlet excited state. Ground state is also anti-parallel, they are spin paired, but when an electron has moved to the LUMO level, from HOMO to the LUMO level, the spin are opposite to one another. See, this is facing up, this is facing down. This is called a singlet excited state. It can immediately return back to its original position, giving some amount of photon out, and this is a very, very fast phenomena. However, there are certain anomalies, aberrations that happen when you have the same spin appearing at a LUMO level, strictly not LUMO, below LUMO, and this is called a triplet excited state, and this is an aberration, this is an anomaly. This has the exact same spin as this electron. Why am I talking about this? Because unless this, if this returns to its original position just like that, it will be violating the spin rule. This can very strongly return back to its original position and it will be in a ground state, but this cannot. Meaning, if you have been able to excite an electron from lower level to higher level, at higher level somehow you have been able to turn its spin, it will have difficulty returning back home. It will have difficulty returning back to the ground state. What do you think would be the manifestation of such an anomaly, where it would like to dissipate the energy, that is its nature, but simply cannot because it is not allowed back home because of its bad spin. This overall diagram can be considered as a very, very rough version of Jablonski diagram. This is the basic of fluorescence and phosphorescence. We will be discussing fluorescence and phosphorescence in coming chapters. This, when the spin is paired, the spin is opposite and it returns back very easily to its ground state by emitting a photon, gives rise to fluorescence. Okay? You hit light, electron moves up, then electrons comes out, gives out some amount of electron. This is phosphorescence, where after hitting it with light, you have switched off the light, but it will keep on glowing. It has to dissipate it somehow. You might think of dissipating it as phonon, but phonon is also out of reach for this particular case because of the spin. So, you might have seen those, previously we used to call radium watches, which glows in the dark. That actually uses phosphorescence. Anyways, we will discuss phosphorescence at a later stage, but let us discuss what actually happens when we excite particular electrons in specific molecules. So, we have two nucleuses. They are separated by a distance r1. Okay. You have a molecule made up of two atoms, very simple hydrogen atoms. Hydrogen 1, hydrogen 2, identical atoms. They have formed the diatomic molecule H2 and they are like this. They have a separated distance between their nucleus. Their nucleus are separated by a distance of r1. Frank-Condon principle states that if you are exciting these atoms with energy, light for example, since we are discussing with light, the time taken for electron to move, electron to get excited is much smaller because it is so light than the entire nucleus, because the nucleus is obviously heavy. You might think this is common sense, but there is a manifestation for that. There is a very strong manifestation to that, and that is described in this Frank-Condon principle, which we are going to see how they help us in emitting of light. So, again you have two diatomic molecules, well, a diatomic molecule hydrogen and hydrogen separated by a distance r1. You have now excited just one of them, just one atom of them with an energy with some amount of light. So, what will happen? The electron of one of the hydrogen atom will go to the next level, will go to the higher energy level. So, if it has moved to higher energy level, if it has gone to the next quanta, the next level, wouldn't the size of the diameter of the atom increased? Previously you have nucleus and you have the electron cloud around it. Now the electron cloud has gone to the next level. The electron cloud has now gone to the next level. So, overall the diameter has changed of the individual atom, but since it takes nucleus more amount of time to move, they have not separated per se. They are still in this particular case where the electron cloud of one is now almost overlapping a certain section of the electron cloud of the other. Remember, we have only supplied energy, only supplied light to one specific atom. This has not been touched. This remains untouched. This has been touched. Energy has come. Its electron has moved to upper level. Its electron has moved to upper level, and thereby this has swollen up. This atom has swollen up, and this electron cloud is now almost overlapping a portion of the original atom's electron cloud. So, what will happen if two electrons, or since it is hydrogen there are two electrons, are overlapping one another? There will be a force of repulsion between them. Okay. There will be a force of repulsion between them, resulting in some kind of a separation. This will force, there will be mutual repulsion between the electrons which were overlapping each other to separate. They have now separated. Now they have separated. It took some amount of time because it is not instantaneous. The electron has moved, but the nucleus is still there. But now one more force, the repulsive force between the two electron clouds have come back, and it has separated it through. After some time, because of spontaneous emission, this will lose the photon and come back to its original position by emitting a light. However, the nucleus has still not moved because nucleus is heavy. Nucleus takes time to move. Thereby, the internucleus distance have now moved from R1 to R2. Though the excited state has gone away, yet the separation distance between the diatomic molecule are different than it was in the original position. Now, obviously, in this particular case, after some time the restoring force will come into effect and it will revert back to its original position. Why is this important? Frank-Condon principle allows us, gives us time, because electron and nucleus moves at different timing. This and this are the intermediary phases. These are the phases that happens in between absorption and emission, and all of them has manifestation when we are trying to identify, mark my words, this is very important, when we are trying to identify, trying to sense, trying to detect a very, very specific molecule, right. Different molecules will have different R1 and R2, different time where it can stay at R1, different time it takes to go to R2, different time it takes from R2 to relax back to R1. These are the characteristic feature of individual molecules. If we can identify these telltale signs, what is R1, how long it stays in R1 after absorption, how long it stays in R2 after emission, how long it takes it from coming from R2 to R1 after relaxation. If we can identify these telltale signs, if we can identify all of these structures, they are very, very specific to specific molecules, we can somehow get closer in detecting what are the molecules. Trust me, this happens, this is a requirement when it comes into conjugated molecular materials, when we are dealing with a hugely complicated compound. Think about chloroform, think about DNA, think about RNA, think about a virus, think about a cell. What are the different molecules that are available that makes up this entire human biological cell? And if you want to identify each and every individual molecule that makes up this entire cell, entire virus, entire RNA, you have to start from somewhere. Might well it be this. This is not the only one, but the significance I am telling you, the point that I am making here is that Frank-Condon principle will be useful when you are going to understand the emission and the absorption part, as well as perhaps in identifying, detecting, tagging a particular molecule. So, the energy level diagram in terms of R1, R2 and the excited state, ground state can be considered it like this. This is I am repeating it. Do not worry about why I have made it bent. Previously I was making straight lines, but you understand that energy bands cannot be simply straight flat away. They cannot also be bow shaped like this, but this is something to do with EK diagram, energy versus momentum diagram. Any physics textbook will tell you why this is bent or why this is a representation. So, excited states once again has several subatomic suborbitals, ground state have several suborbitals. Depending on what kind of frequency of light being absorbed and where the electron is going from the lowest of ground state to the highest of excited state or something intermediate, you get different bands of frequencies that it can absorb. See, that is what I am saying. Since you have a very thick band, depending on whether this electron is going here or here, different levels, different photons are getting absorbed. And quite similarly, when you have emission, depending on from which excited state suborbital the electron is falling onto the ground state suborbital, give rise to different values of emission. Usually this is at higher frequency, it loses some amount of it by non-radiative decay, non-radiative emission, and similarly when it has reached to the ground state, it also loses some amount of energy in non-radiative emission. Depending on where exactly in the ground state it is coming, from which particular excited state suborbital, we have different bands of emission. They can usually merge together, and in experimental spectra you get something like a very flat band. So, absorption is from this to this region, emission is from this to this region. You can ask yourself this question, what happens in this region where absorption and emission spectra are overlapping? This is a typical absorption spectra of conjugated material. Spectra simply means wavelength, which is frequency, which gives rise to energy, and the intensity as in how much of it is absorbed and how much it is emitted. So, you can see around 500 the absorption of this conjugated material is very high. 500 is where any light, any electron will move from lower level to upper level, and it start emitting at 600 nanometers, and then the emission rate starts falling. Basically, what I am telling you is that unlike silicon or any other semiconductor material per se, the overall moral of the story is there are several sub bands, there are several orbitals, molecular orbitals inside each single band, and depending on which position of the band the electron is jumping to which position of the ground state, you get an emission. Usually we send a bunch of photons and we get a bunch of photon emitted. They are at different wavelengths from another. Some of them may overlap, some of them will not overlap. A significant use of that is in fluorescence microscopy, where we add fluorophores to certain areas of cell or viruses, subcellular parts, DNA, etc. We bombard them with a high frequency laser, say blue laser, ultraviolet laser, and it start emitting light in green or in red part of the visible spectrum. Thereby we can see it. Thereby we can observe where this light is emitting from, and from our microscope we can observe what exactly is going on. Next class I will be discussing about fluorescence, how it has revolutionized biology per se. Here in fluorescence you will see the first glimpse of biophotonics, or what biophotonics can actually achieve. So, the concept covers here are again HOMO and LUMO, singlet and triplet, absorption emission along with Frank-Condon principle, and please go through the optical properties of solid book. It is a very interesting book, very nicely written, and you can start from any level to understand it, not very much maths intense. So, even medical students or anybody who dislike maths can simply go through it, understanding the basic of light matter interaction. And as always, Introduction to Biophotonics by Professor Prasad has been my companion throughout. So, thank you very much. Next class will be just fluorescence, and I will finish the revision of light matter interaction. Please write your comments below. I will try to modify my lecture accordingly. Thank you very much.